Hello everyone. In this video lecture, we are going to see some of the topics in the module 3 of microcontroller and embedded system subject. In the previous class, that is previous video lecture, we completed embedded system definitions, history, classifications, and major purpose and applications. In this video lecture, we are going to see core of an embedded system. We have to refer Shibu KV textbook name is Introduction to Embedded System. Core of embedded systems. We have embedded system classification in the previous classes, but here we have four core main divisions of embedded system. They divide into four types, that is, one is general purpose and domain specific processor, second one is programmable logic devices, short form is PLD, third one is application specific integrated circuits, ASIC, fourth one is commercial off the shelf components, COTS. Here general purpose and domain specific processor are again subdivided into microprocessor, microcontroller and digital signal processor. Let us go for first one, general purpose and domain specific processor. Here name itself specify that general purpose, that processor we can use for general purpose or that processor we can use for specific purpose. That entire this general purpose and specific purpose processor are again subdivided into microprocessor, microcontroller and digital signal processor. Let us we go for first one, microprocessor. Name itself tells that it is a processor with the size of micro, that is 10 to the power of minus 6, very small device, and that device is made up of silicon. A chip, silicon chip contains only CPU. Here we have definition, a silicon chip representing a central processing unit which is capable of performing arithmetic as well as logical operations according to predefined set of instructions which is specific to the manufacturer. Here one device or microprocessor means one small chip that is made up of silicon that contains only CPU, that is central processing unit. All the related or required devices like memory, input output devices or counter, control unit or timer, everything connected outside the silicon chip, but in the silicon chip we have only CPU. That device is called, or that chip is called, microprocessor. The CPU only is there in chip. So what is there inside the CPU? One is arithmetic and logical unit, second one is a control unit and working register. These three things are there inside the CPU. Arithmetic and logical unit which performs arithmetic operations and logical operations, and this is a computational unit for CPU. And control unit which is used to control this ALU and registers. And register is a temporary memory and used to store some data values. Lot of registers are there inside the CPU. Some of the examples, some of the companies they developed microprocessor. One of the company name is Intel. That you aware of that company Intel? They developed the first microprocessor. Again till now we have lot of microprocessor developed by Intel. Then we will go for microcontroller, a highly integrated silicon chip containing CPU, scratch pad RAM, special and general purpose register, on chip ROM for program storage, timer, interrupt control unit and dedicated input output devices. Here thing is, we have one chip that is made up of silicon, and that chip contains CPU, RAM, ROM, timer, control, that means control unit, input output devices interrupt control unit, everything is there in that one single silicon chip. Now microcontroller can be considered as superset of microprocessor, because you know microprocessor contain only CPU inside the silicon chip, but microcontroller contain everything, all the devices including input, output, memory, everything is there in a single silicon chip. So this is a very superset of microprocessor. We have a lot of devices which develops microcontroller, and we have different types of microcontroller. ARM is the recent trend is ARM, and first one is a 8051 microcontroller. Then we have AVR microcontroller, then PIC microcontroller is there. Now we have ARM microcontroller. So ARM microcontroller, we have that topics in the module 1 and module 2. We already discussed about that. ARM full form is Advanced RISC Machine. RISC specify reduced instruction set computing. Here microcontroller, lot of devices are there. That means Texas Instrument, microchip, silicon chip, like this many companies, and Texas Instrument is one of the famous company. Another one we are using in our lab, that is LPC 2148, that is developed by NXP company. Like this many companies, they are developing microcontrollers. We have very important topic, that is a difference between microprocessor and microcontroller. One of the definition we already seen in the previous, one of the difference, that is a definition. So microprocessor contain only CPU and remaining all devices connected outside the chip, but microcontroller, in the single chip we have CPU as well as all the other devices, all the other items, that means memory, input, output, everything connected inside the one chip. And second difference is microprocessor is a dependent unit, but microcontroller is not dependent. Here dependent means because that only contains CPU, right? So remaining all devices it needs for proper function, but that all devices connected outside. So without that devices microprocessor won't works properly. That's why it is dependent unit. But microcontroller is not dependent that much, because everything is there in that single chip itself, memory, input, output, everything. Third one, most of the time general purpose in design and operation. That means here microprocessor normally we are using as general purpose itself, but microcontroller, that is normally we are using for specific purpose. Then next, doesn't contain a built-in input output port. That means we know that we connecting input output outside here, but in microcontroller we have that inside itself, inside the silicon chip. Then power saving option is the limited power saving option. That means limited power saving option compared to microcontroller. In microprocessor it consumes somewhat much power, but here power consumption is better than microprocessor. In microcontroller power consumption is better than microprocessor. We can save power like battery. Application specific instruction set processor, ASIP. What does mean this? Here name, you can see this name, application specific. So this processor having some instruction set, and that is used for particular application. We can read this: application specific instruction set processor are processors with architecture and instruction set optimized to specific domain or application. We are using for particular application purpose, like networking or automotive or telecom, media, digital signal processor, control application. Like this particular purpose we are using this ASIP. Digital signal processor, this is another type. Digital signal processor is powerful special purpose 8-bit or 16-bit or 32-bit microprocessor designed specifically to meet the computational demand and power constraint of today embedded audio, video, computational or communicational application. Here digital name itself, a processor used for processing your signal, digital signal, that is called digital signal processor. Your thing is digital signal processor are actually 2 to 3 times faster than general purpose microprocessor. General purpose we seen in the previous, that is used for any purpose, but digital signal processor also one of the microprocessor, one of the type, but it is more faster. It is 2 to 3 times faster than general purpose processor. It is more fast, that's why we can use this in many of the application. Mainly we are applying this processor for signal processing applications. Inside digital signal processor we have some of the components. One is program memory, one is data memory, computational engine, input output unit. What do you mean by program memory? This is a memory for storing your program. Here we are going to store program or code in this program memory. Next we have data memory. Data memory, it is a memory used to store data. Then computational engine. This computational engine is a used, that is like ALU, logic, some operations we are going to perform in this computational engine. So what type of operation? We are going to take program or code, that program and code is there in program memory, that we are going to take and perform operation on data. So both things are there, which instruction which specify your that is the instruction is there inside this program memory, data is there in data memory. So you are going to perform particular operation on that data. Operation is there in that instruction. So that operation will perform inside computational engine. Next we have input output devices. Here we are, this is name is digital signal processor. We need signal as a input. We need signal as a input. That is the data, we have signal. How to capture that signal? Or input output device means what? This is a device which is used to communicate with external world. You are going to take data from external world and you are going to give it to embedded system, that is a DSP system. What is that data? That is a signal. So input output devices, some devices used to capture the signals and giving to this embedded system, and once that computation is over, some of the devices again gives that signal, that is after computation we are getting some result, that result is giving to again external world by using output devices. So input device will capture, output device will give that result to outside world. This is mainly used in some audio video signal processing or telecommunication processing. Okay, there we are using this DSP processors. Another very important definition or difference. What do you mean by RISC and what do you mean by CISC? This is the actually definition. RISC and CISC definition is important. RISC full form is a reduced instruction set computing. CISC full form is complex instruction set computing. What is the difference between this and RISC and CISC? RISC is having lesser number of instructions. CISC is greater number of, more number of instructions are there in RISC or CISC. Which one? CISC we have greater, but RISC we have lesser. Small number of instruction number is less, but also reduced. What do you mean by reduced in instruction set? Here actually complexity is less. Complexity of the instruction is less. What do you mean by CISC? Complexity of the instruction is high. instructions are complex. In the RISC, instructions are simple instructions. Second one, instruction pipelining and increased execution speed. Here we can perform one operation, that is a pipelining. Pipelining operation is used to increase the speed of the processor. That operation we can apply in the RISC concept, but CISC we can't apply that concept. That is a pipeline will not work in the CISC. Then again we can go for some of the main differences between RISC and CISC. We already seen this RISC CISC difference in the module 1. This is a very important. This concept is there in module 1 and module 3. Any one of the module you will get this question, RISC and CISC difference. And another difference is fixed length instruction. In the RISC, reduced instruction set computing, we have all instructions are same size, but here in this is all instructions are different size, that is a variable length. And Harvard architecture, we are going to discuss this in the next slide, so I will explain in that slide itself. So here RISC which uses Harvard and CISC can be Harvard or von Neumann, maybe both. Okay, either out of this any one of the concept used by CISC. At a time that can't use Harvard and von Neumann, any one of the concept can be used by CISC, either Harvard or von Neumann. Silicon usage also less in RISC, CISC it is high. Like this we have another one, large number of registers are available. Here RISC number of registers are high. In the CISC limited number registers are there. That register, again I am talking about general purpose register, special purpose registers are there in both RISC and CISC. Here general purpose registers I am talking about here. In CISC very small number of general purpose register, but in RISC lot of general purpose register we are using for our operation. Next we are going for Harvard and von Neumann processor or architecture. It is a memory architecture. We can go for Harvard architecture or von Neumann architecture. You can see this diagram here. The first diagram is for Harvard architecture, second diagram is for von Neumann. What is a Harvard architecture? In the first line they given separate buses for instruction and data fetching. Bus which is used for communication purpose. Bus, another thing is set of lines. Bus means set of lines. Separate buses used for instruction and data. Fetching means capturing the data from either external world or we can capture the data from memory also. That capturing by using buses. Okay, we are going to take that data or instruction from the memory into your processor. At that time we need buses. That bus may be instruction or data. We have two types, right? Instruction, that is the programs, or data. We have two types of buses. For each, you can see this diagram. Here program memory is there. Here it contains lot of instructions. Data memory is there. Here we have lot of datas. Here we have separate bus. Harvard architecture means for data memory we are using some set of lines, that means buses. Here we are using one bus. For program memory we are using separate bus. So separate buses are there for program memory and data memory. This concept is called Harvard architecture. But von Neumann architecture means memory is only one. Memory is only one. In that we are going to store both program and data. Only one memory is there. So here only one bus is there. In that bus both program, that means instruction and data fetching will occur by using only one bus. Easier to pipeline. In the Harvard architecture, easier to pipeline. Pipeline is easy here. So high performance also high. Comparatively high cost. Which one? Von Neumann is cheaper actually, and this one is cost is high compared to this. So, here low performance, which one? Von Neumann is a low performance compared to Harvard architecture. The last point, since data memory and program memory are stored physically in different locations, no chance of accident. There may be no chance of accident because separate buses are there for program and data. There is no chance of accident between your programs and data. That means instruction and data. Separate buses are there for communication purpose. But here there is a chance of accident because only one bus is there. In that bus we are going to transfer both your program and data. So, there may be a chance of corruption. Another concept is big endian and little endian. This concept we already studied in the laboratory also, and first and second module also. Big endian and little endian processor. In one line we can define that little endian concept. Lower order byte of the data is stored in memory at the lower address, higher order byte at the higher address. I told in the previous module, low to low, high to high, that is called little endian. Low to high, high to low, that is called big endian. Again, big endian concept is higher order byte of the data is stored in memory at the lowest address and lower order byte at the highest address. This concept is called big endian. This is very much important in the microcontroller and microprocessor operations. Next we are going for load and store operation. What you mean by load and what do you mean by store? Loading from where to where? We have one side memory, one side we have registers. Registers present in CPU. Memory is there outside. So, memory to CPU we have to take some of the data or instruction. We have to fetch the data or instruction from the memory to CPU. At that time we are going to use concept called load. Store means whatever data present in CPU. Now, after operation some data is there in CPU. That data we are going to send it back to memory. That process is called store. This is very important process, load and store in embedded system and also microcontroller, microprocessor. The RISC processor instruction set orthogonal or operate on a register. That means we have memory and register. Memory access related operations are performed by using load and store. Here you can see this diagram. Here we have three registers and one ALU, arithmetic and logical unit. Here this is the memory part they shown here. Now we have to perform this operations. The given code load R1, X, load from memory to register. Here we have memory. We have to load X value we have to load inside R1, loading from memory to register. Another concept load R2, Y, take value of Y, that means the second value from the memory to second register R2, memory to register concept, load. Add, we can perform add operation inside your CPU itself or processor. So, we are going to take that value inside your processor, perform operation. Once operation is over, send that output back to memory. In order to perform operation, we are taking that data inside processor. Here you have data in R1, you already fetched the data in R1, R2 also we have data. You are going to add that data. Operation is add R3, R3 is destination, R1, R2, that means R1 plus R2 we have to perform, then answer is loaded in, that means we have to move in R3, R3 is the destination. Then we have now answer in R3, we have to store back. Storing means from register to memory. Store R3, Z. R3 we have data, store that thing to memory, that is a storing operation, register to memory. Another concept is instruction pipelining. Pipelining is used to increase the speed of the processor. Here the conventional instruction execution by the processor follows the fetch, decode, execute sequence. We have to perform some operations. That means a processor needs data from memory and processor need instruction from memory. Both instruction and data is there in memory itself. You have to take that. That is by using fetch. Fetch is the operation for capturing the data and instruction from the memory. Then we have to perform decode operation. Then execution. Execution is there in your CPU itself. And you can perform another operation, store back. That means whatever we got answer in after execution, that answer you can store back inside memory itself. Here fetch, decode, execute. How we are going to perform? Here you can see one diagram. Here they consider only two stages, fetch and execute. First, non-pipeline. What do you mean by non-pipeline? If that non-pipeline means fetch is occur, once that fetch over, then another stage, that is execution, will occur. Once that execution over, then next again fetch will occur. So each stage waiting to complete previous stage. That will lead increasing in the complexity of the overall operation, or it will increase, it will not increase your speed of the processor, it will decrease your speed of the processor. That is why we are using pipeline concept. Here you are going to perform fetch operation, then it goes to execute. So here you can see fetch program counter. That means one instruction is fetched and that particular instruction goes to execute stage in the next clock cycle. Okay, this PC will goes to execute stage here. At that time, when your first PC is there in execute stage, you are going to fetch next instruction. Next means PC plus 1. When your current process or your current instruction is executing, next instruction going to fetch. When this execution is completed, at this time this PC plus 1 will goes to execute stage here. When your PC plus 1 is there in execute stage, your immediate next instruction, that is PC plus 2, will fetched. This concept is called your pipelining. This will increase your speed of the processor. Very less clock cycle time is required for this operation. Again, PC means program counter. Program counter will store address of the next instruction to be fetched. We have another concept called application specific integrated circuit. This is another format of core of the embedded system, another classification, we can tell it as classification also. ASIC short form. A microchip designed to perform a specific or unique application. This is also chip, small chip in micro size, and that chip is not general purpose. In the previous case we seen general purpose, but this chip is not general purpose, that is used to perform some specific, or you can call it as a unique application. We can use for only one purpose. It is used as a replacement to conventional general purpose logic chip. We are not, this is not general purpose, this is application specific. ASIC integrates several functions into a single chip. Many functions we can, many programs we can dump into one chip, but that once you design, that chip will perform only that operations, only that application, that you can't change that. Reduce the system development cost. Cost is reduced. System development cost, once you design, then that is fine. There is no much cost for development. Consumes very small area in total system. Very small chip, right? Microchip is there, so size of the microchip is small, so consumes very small area. design of smaller systems with high capability functionality. Smaller chip is there and several function is there. That is the second point. Smaller chip with several function, that will increase your performance of the device. Efficiency increased, okay, through output increased. So this is the application specific, used for particular purpose. Another device we have that is a core of the embedded system is programmable logic devices. Logic device provides specific function including device to device interfacing, data communication, signal processing. This is a device we seen in the previous semester, that is you can remember that PLA, PAL, PROM, that concept is coming under this PLDs. PLA, PROM, PAL, that is programming array logic, programming logic array, and PROM concept. Like that we seen some of the problems also in the previous semester, that is in analog and digital electronic subject. That is coming under PLDs. Here which is used for this PLDs, used for data communication, signal processing, data display, like this some of the applications are there. Logic devices, we are going to use a lot of logic devices here, means logic gates, logic transistors we are going to use to build these logic devices. But they given one thing, programmable. We can program, we can edit, we can modify that particular logic devices. That's why they given programmable. Otherwise you can't edit that. If they given programmable, user can modify, user can edit that. Here we have logic devices, that means this one divided into two types, fixed and programmable. Fixed logic devices and programmable logic devices. Here fixed logic devices means once you programmed, you can't change that program, that is a fix. No one can modify that, no one can edit that. But programmable means logic devices programmable, that logic devices we can edit, we can program, we can reprogram, we can modify, like this, that is a programmable. Two major programmable logic devices, they explain this one, programmable. In that we have two types, one is CPLD, another one is FPGA. Your second one is a very important, FPGA. First one is CPLD, complex programmable logic device. FPGA means field programmable gate array. We will see that one by one. First we will go for CPLD and FPGA both. Now FPGA. FPGA is a IC. This is a IC actually designed to configured by the designer after manufacturing. FPGA offers highest amount of logic density. Lot of code we can dump into that device. Highest code density is actually high, logic density. Okay. The most features, lot of features are there in the FPGA and performance also very high. So that is the advantage of FPGA. Now these advanced FPGA devices also offers features such as built-in hardware program, substantial amount of memory, clock management system, and support for many of the latest very fast device to device signaling technology. Latest fast device to device signaling technology, we are using this FPGA concept. Another one, FPGA are used in wide variety of applications ranging from data processing, data storage, or telecommunication, digital signal processing. These are some of the application of FPGA. Now we have another one, CPLD, complex programmable logic devices, CPLD. It is a programmable device with complexity between PAL. We seen this PAL, programmable array logic, and FPGA, that is Field Programmable Gate Array. And architectural feature of both. Complexity is not that much PAL and not that much. In between these two, actually this complexity of PAL is small, complexity of FPGA is high. So, between this we have complexity. CPLD offers very predictable timing characteristic and are therefore ideal for critical control application. In order to use this CPLD in critical control application, we need perfect timing. If the timing is predictable, then only we can use that for some of the complex applications. Here we have that. It is very predictable timing. It have very predictable timing character. That's why we can use this CPLD in complex applications. One of the devices is this one, Xilinx Cool Runner series, also require extremely low amount of power. Actually, this require low amount of power, are very inexpensive, making them ideal for cost sensitive battery operated portable applications such as mobile phone, digital handheld assistants. We can use this Xilinx Cool Runner. Xilinx is a software. We are using actually this is a device. Xilinx Cool Runner is a CPLD device. There is a hardware device which requires low power and inexpensive, and we are using that for some of the mobile phones and some digital handheld assistant, that means your tab like this. And this is two types, FPGA and CPLD. One of the difference is here FPGA, here we have some of the logic gates. Mainly we can differentiate by using logic gate itself. I told we are using some logic gates here, there also we are using logic gates. PLD means using logic gates, we are going to build that PLDs. In this FPGA, the logic gate numbers are 1K to 500K. Okay, that much logic gates we are using inside this FPGA. But in the CPLD, up to 10,000 logic gates we are using. Up to 10,000 logic gates we are using to build this CPLD. So, this is somewhat complex. CPLD are complex, but complexity is in between PAL and FPGA. That is another thing. Now, what is the advantage of PLD? So, in the previous year, we have two types of PLD. We seen that programmable PLDs. But what is the advantage of PLD? This one, previous slide we seen here. What is the advantage? Actually, here flexibility is good. More flexibility is there, and timing characteristic also good, and no need to invest in order to design or in order to build PLD. We need very less amount of money. Okay, cost is less, building cost is less, so no need that much cost in order to prepare this PLDs. Initial cost is very less. Another very important thing is programmable. That is the advantage. Programmable means you can reprogram, you can modify. That is one of the major advantage of PLD. Then commercial off the shelf component. This we are going to see in real world also. Many of the devices we have COTS. What is this? A commercial off shelf component means a product is one which software or hardware device. We have software or hardware product that are really ready-made available in your market. For example, Microsoft Office, it is actually software tool, and that is a software COTS, software COT. Okay, so COT means it is already available, it is already prepared, it is already manufactured and available in market. you can use that for any purpose. Either that particular device is for specific purpose, you can join many of the hardwares, many of the cards, and you can build one larger embedded device also. Advantage, they are readily available in market, cheap, very cheap, and developer can cut down development time great extent. That means less amount of money is required to buy this. There is no need to design the module yourself, because already it is designed and already it is available in market. We have both type, okay, software also there, hardware cards also there. Software cards, they give an example here, that is Microsoft Office. Hardware, we have lot of things, you can get that in hardware shops. Everything will be ready supplied by the card manufacturer, everything is already prepared. But drawback is that is a update, you can't update that. See, manufacturer may withdraw product, means discontinue of the production of the cards at any time if rapid change in the technology changes, that you can't update that same device is there in market. So but new devices came, means you don't have a demand for that particular previous card, right? So that's why here, as technology changes, they are going to produce new commercial off-shelf component devices. In the next class, we are going to see some of the concept related to memory. Thank you.